So what I have here is just screenshots from our Animal Cloud. This algorithm is also available in the open source, by the way. And we have a way to measure a covariate shift that just takes into account the entire model input data structure. So we just measure how strong the data structure changes. We also have it described in details. It's called PCA reconstruction error. I won't be going into detail here. Suffice to say that it's a way to measure the strength, the magnitude of covariate shift in one number. And we see here that we don't really have a strong covariate shift because it doesn't change from the test set. And test set is kind of our reference set for which we always assume that everything is fine. So if this value is fine for the test set, then we also, once we put it in production, this part is the production value, the value that we haven't seen, then the predictions that we did not train on, did not test on, these are actual numbers that we use to make predictions in reality. We see that this PCA reconstruction error, so the measure of covariate shift is not really changing. And if that's the case, so we don't have very strong covariate shift, but we have some kind of covariate shift, we do see that CBPE is great at estimating accuracy. And you see that it basically the line of estimated and realized accuracy follows perfectly. And there's also one very interesting thing to see that even if we don't have covariate shift, we can still see a significant drop in performance, and the drop in performance is really significant here. It drops by almost 10 percentage point. 10 percentage point change in accuracy is definitely something that the business should know about. So we see this drop in accuracy here, which is also another reason why you always need to estimate performance and not just rely on data drift signals, because your data drift signals can be quiet and there's still significant issues. And of course, vice versa, there might be potential issues with covariate shift. There is some kind of covariate shift, but it actually doesn't impact performance that much. But we see that for small covariate shift, CBP works reasonably well. Now, let's take a data set. These are all real life data sets. And we see that there is some kind of strong covariate shift around beginning of July, let's say. And here, CBP is able to detect that there is indeed a change, but it underestimates that change quite significantly. So it only detects one batch of data where the change was actually significant enough to trigger an alert, whereas the problems actually already started a few batches ago and they are stronger than expected. So it is directionally correct. It tells us something. It is still useful, but it doesn't tell us the full story, and it might not be enough if our use case is very important. We also see the confidence bounds would tell us possible range of performance. This is something I won't be covering here, but we also have an algorithm that estimates this this confidence bounds. And we see for 2 points, it actually goes out of the confidence bound. So we see that for strong covariate shift, also these confidence bounds cannot be fully trusted. So we see that there is an issue with strong covariate shift. Now, we already talked about that we have potential assumption that we're violating about calibrating the model, and the model is only calibrated and can be only used to do this magic trick when we take the predicted probability and transform it into performance if there's no strong covariate shift. So let's measure how it actually impacts calibration. So what you see here is the same calibration curve that I showed a few slides ago, but just for this model that we trained that you just saw above, on the first data set on the analysis data, so we're only showing it how it actually behaves after the model has been deployed. And the calibration here is basically perfect. It's still like slightly S-shaped, but nothing to worry about. This is good enough. Whereas if we look at the second data set when we experience very strong covariate shift, and I was actually surprised, like properly surprised to see how bad it gets. I was expecting that it's going to be like more S-shaped than this one, and it gets miscalibrated a bit, but we see that calibration here is absolutely terrible, even though we did calibrate that model on our test data. But once it's been deployed, we've seen that the calibration is completely ruined, and we should not be using that to estimate performance. We did, and we still got some kind of information. So we see that CBP is in some ways a bit robust to covariate shift, but once covariate shift gets strong enough, it starts to be very inaccurate. And one note here is that the effect of this miscalibration performance is complex. It's strongly nonlinear. You cannot really just draw any kind of simple way that you measure some kind of calibration error here and then you try to push it to performance error. There's few more things there. It's also a very nonlinear effect. So let's kind of finish looking at CBP by looking at the last thing, which is how well does it handle small data. Sometimes we won't have the luxury to actually have access to few thousand data points per every chunk. Maybe we get only a few hundred data points every week, and we really need to know the performance of our models every week. How does CBP deal with that? Here, there's good news. We actually see that CBP, if we take a data set and we chunk it, or so we use batches of 250 data points, the data set is actually, the CBP is actually very good at estimating those. If we use bigger chunk size, then the data set, the CBP is still equally good at estimating those changes. So if we want to work with small data, we can use CBP. And these screenshots are, by the way, I think from our open source, so it looks slightly different just for a bit of variety added. So now let's talk about how can we potentially solve the problems with not having good calibration. And the way to do it is try to calibrate potentially with respect to many things at once. But before we go there, let's try to kind of understand how is it even possible that we calibrate our model, then we see no concept drift, so the actual pattern between the model inputs and the targets does not change, but we still lose calibration. And I'm going to give you a simple explanation here. So imagine we have a feature in our data set, which is a binary feature, and it can have value either blue or red. And it just so happens that 90% of the data points in our data set are blue, and the remaining 4 are red. Then we're going to calibrate our model. And because I mentioned that the calibration only gives us guarantees on the average, we know that for the average calibration, let's say we get like actual perfect calibration, but it might happen that the blue, if we take just the blue segment of the data, which is 90% of our data, it's going to be slightly miscalibrated. It's going to have a shape like that. And for the red part of the data set, it's going to be terribly miscalibrated. It's going to be like the predicted probabilities won't really mean anything. And the good news is that on average, when we construct our partial confusion matrix or instance level confusion matrix and we start adding things, these errors will even out. And as long as we get calibration that's good on average, we're also going to get estimation that's good on average. However, imagine now that we undergo covariate shift, or the dataset undergoes covariate shift, and what we see is that now we have 90% of red values, but only 10% of blue values. Right now, the miscalibration of blue segment and the red segment does not cancel each other out anymore. And together, on the average, we actually see that the dataset has become very strongly miscalibrated. And this is kind of the intuition of why just pure covariate shift can actually influence calibration, and why that might mean that CBP will stop working as well as it used to. So how can we solve it? The simplest way to do it is we can look at all our segments in the data, all categorical features, and we can potentially, if our data is big enough, try to calibrate each of those segments separately. Then even if the composition of those segments shifts as we deploy our model to production, we have nothing to worry about because they are all separately calibrated. Unfortunately, this is literally impossible in practice. And there are multiple reasons. First of all, how do we use continuous features? The data can also shift along the continuous features. Maybe first we were dealing with a population that was mostly in the 20s. Now our customer base is mostly in their 40s. What do we do with that? How do we segment that? How we try to calibrate with respect to different segments at the same time? We need to impose arbitrary lines. And if the range of this continuous feature is big enough, we might not be able to have enough data to actually do proper calibration, because remember, it's still a regression model. We still need to have enough data, generally speaking, at least 1,000 points to fit it well. What about imbalanced features? If we have a categorical feature and one of the categories only happens in 0.001% of the cases, we're almost guaranteed to not have enough data for that specific segment to calibrate it separately. And last thing is that the covariate shift might happen not along an axis of one specific feature, but it might happen along the combination of features. So the only thing that drifts is, for example, that we have more people who are at the same time old, rich, and green, for example. Then again, if we look at this subset small enough, we will never have enough data to actually calibrate it. And there is a solution, but before I go into the solution, let's try to figure out a different approach that will actually give us the tool to solve this problem. And this different approach is importance weighting. So importance weighting is a surprisingly simple algorithm that's surprisingly hard to explain for me. And it only takes 2 steps. So before I go over the steps, let's first talk about what we intend to do. So what we intend to do is we're going to take our test data set, and then we're going to try to reweigh the performance on that set so that it somehow resembles our current batch. So we're going to weigh higher the data points in our test set that look like the data points in our current batch, and we're going to assign a lower weight to data points that look different in our current test set than our current batch. So we're going to basically assign some kind of importance, the weight, to every data point, and then we're going to use our label test set to just compute performance. And of course, the big part here is how do we assign these weights? How do we even try to quantify this change in distribution in a way that we can come up with those weights? And these are the exactly 2 points. We're going to try to quantify that change in distribution. And again, here you see just 1D example, but we might be dealing with thousands of dimensions, so it's not going to be that trivial. And then another thing we're going to do is we're going to reweigh every point in the test set by how important it is. I know it's vague for the current batch, and then we're going to just calculate the performance kind of as if the test set looked like the batch. So let's get started with the first part. And the way we're going to do it is so-called density ratio estimation. So the kind of explanation is in the name. What we're trying to do is we're going to try to estimate the density ratio, the ratio of densities of the test set and the batch data for every data point in our feature space. And it's important to notice that we cannot just assume that the data points will occupy the exact same spots. So we need to have some kind of function that will be able to tell us this density ratio for any point in our model input space. So we will need to train some kind of model that will approximate this ratio, because we won't have data in exactly every point in our data, in our model input space. So how do we do it? Just a small tangent before, we could alternatively just try to estimate the densities for each of the data sets. So the test set and our current batch, and then we could divide one by the other. But that is a bit more unstable, because if we have very little density from one of the data sets and we divide by it, then we're going to multiply the errors and we're going to get very unstable predictions that don't really work well in practice. So instead, we're going to try to directly estimate this ratio. How do we do it? We start with a binary classification problem. We're going to discard all the all the labels, because remember, for our current batch, we don't have access to the labels. We're going to try to estimate the performance without having access to the labels. This is always an issue. So we discard all the labels. Then we're going to say that if a data point comes from the test set, this is a negative class. If it comes from the current batch, it's a positive class. And then we're going to use all the model inputs as features. And then we just train the model. So we get the probability that a given data point belongs to either the test set or the batch set, given all our model inputs. And then we're going to compute the function from that prediction that will actually give us these density ratios. And we're going to do it step by step here. This is the part that's slightly complex, so bear with me. What we need to do to compute this weight is 2 elements. The first element, which is kind of easy to understand, is that what we need is we're going to basically take the probability that a given class belongs to the batch at any given point, and we're going to divide it by the probability that this specific point, given x, belongs to the tests. So we basically just divide this value by this value, which is what you see here in the visual explanation. And another thing that we need to do is we need to normalize by the number of data points in the test set and the batch, because if we don't do it, the model is very likely to say that everything belongs to the test set, or it's more likely to belong to the test set. So this can be formally derived using Bayes' theorem. It's not that hard, but here I just want to give you an intuition. So we're going to also divide it by the number of data points in the test set by the number of data points in the batch. And this is the weight we get. And then we're going to use that weight when we just calculate performance. Let's say we calculate accuracy. So every data point, we're going to do it on the test set. And every data point in the test set, for every data point, we're going to calculate this weight. And then we're just going to apply it as the importance of this data point. And we get our metric. So we don't have to talk about probability here. We don't have to talk about calibration. It's a completely different approach. Let's see how it works. So again, I use the same data sets here for small covariate shift. We see that the model performs very well, and sometimes you get like a bullseye, basically. This is a perfect prediction. For very small changes, we get slightly higher error than CBPE, but generally it's comparable. Slightly better here, slightly worse here. It's fine. And good news is that even under strong covariate shift, because we don't have this additional hidden assumption, the model is quite good at predicting what's going on, and it can actually estimate even big changes in performance that happen due to big covariate shift. But there's an issue, and the issue is small data and small chunk sizes. And this is something that unfortunately happens quite often with models in production, that you don't make that many predictions every week or every day. And here, if you see the big chunk size, everything's fine. If you look at the small chunk size, it's potentially not that obvious to see, but you see that the dark blue line, which is the realized performance, and the light blue line, or teal, I think it's called, which is the estimated accuracy, they don't actually follow each other very well, and the model is kind of doing random things. It still follows reasonably well the actual trajectory, but it's nowhere near as good as CBPE, which was basically perfect here. So we solved one problem, but we introduced another. And now, as we slowly get to the end of the workshop, let's try to combine these two ideas. And the way we combine it is the M-CBPE algorithm. And what we're going to do here is we're going to take our CBPE, and instead of trying to figure out a magic well to calibrate it with respect to everything at once, we're going to forget about it, and we're going to just calibrate it with respect to current batch. But we don't have labels for the current batch, and to do calibration, we're going to need those labels. So what we're going to do is we're going to apply importance weighting, not to calculate performance, but to calibrate the model. So we're going to apply these weights that we just calculated. We calculated in the exact same way, and then we apply to our regression model to the importance for every point as we train our regression model to actually calibrate the original model. So we're going to do this calibration on the test set, but we're going to kind of make it look, by applying these weights, as if it is the current batch. And what does it mean is that no matter how the current batch works and how it looks like, we don't need to calibrate it to a million different ways. We just calibrate it to the current batch using importance weighting. And then for the current batch, we have guarantee that no matter how it looks, it's gonna be approximately calibrated. So without calibration on the current batch, if we just calibrate it without these weights, it will look like this. But now we see that there is more blue data points. So we're gonna weigh them more, and we're gonna then get still good calibration. So that is really how we put it together. Kind of a simple thing, but we need to put it in the second part of the algorithm, just only applied to the calibration. So we get rid of this violated assumption, because the calibration is done as if there was no covariate shift, because what calibration sees is the actual current batch and not the test set. And of course, we still need the assumption that there is no concept drift, because we're going to be using the targets from the test set. So the pattern, the concept between the model inputs and the target still needs to hold, even if the model inputs are distributed differently. So we got rid of the caveats. That is we calibrated with respect to something else, so the caveats are actually not problematic, because now the probability distribution is calibrated for the current batch and also for the current covariate distribution, which is exactly what we're interested in. And we're going to do this calibration again for every batch. So it is slightly more computationally expensive, roughly the same as importance weighting, because for importance weighting, we also had to do it for we had to compute these weights for every batch. CBPE is much cheaper because we need to do one big thing only once, which is the calibration. Here we need to compute the weights, which is quite expensive, and do the calibration, which is reasonably cheap for every batch. But let's see if it's worth the additional computational effort or computational cost. We see for small covariate sheet, it's basically exact same carbon copy as here. It's like a small difference, but exactly the same performance. However, for big changes in performance, if you compare it to CBPE, we're seeing that the performance is actually much closer to the realized performance. And the algorithm is able to capture that, and it gives us the alerts every time that there was an actual issue. It's slightly underestimated, but we see that every single data point in our data set is actually well within the confidence bound. And we can actually say that this is a really good way to estimate performance.